Welcome to a lesson with Dr. Powell. We're going to look at how we can compute the work required to pump all the water in a conical shaped tank to the top. Now, what is work? Well, we define work as being the antiderivative or the change of force of, the antiderivative of force with respect to position. So what does that mean conceptually? Well, we want to measure how much work is done if some force is being exerted over a certain range of positions. So let's suppose we have an x-axis which represents different positions, and we suppose we have a graph of force at a particular position. So at this position we have a particular force. Now, how much work was done by that force over those positions? Well, we'll just define the area underneath this curve or area in here as being a nice measurement of work, just by definition. That sounds like a good way of saying how much work is done. Sometimes notions are just by definition or convenient, but yes, that's a nice measurement of the work done. So we just define that area. So let's look at the situation and think, no matter how we do it, all we're doing is we're just lifting this water up just against gravity and bringing it up to this surface. Whichever mechanical method we use to do that will have the same amount of work accomplished, just in our combating of gravity to lift it up. So imagine you had a razor sharp knife here or something that kind of cut the cone as you lifted it up through a particular level or altitude or whatever, and it just runs off the sides right here. So if we do that, we can kind of think of just lifting this cone up and the bottom of the cone being at different positions. So maybe starting at position 0, maybe later on it'll be at a different position right here. Okay, at position X. So notice the amount of work required to lift this cone at any one point is the weight. The amount of force is just the weight of all the water in that cone as we move up, assuming that the cone is full each time. So this modeling situation represents well the definition of work as being area under force, under a function of force, because then we have a specific force at each particular level. So if we think for a minute, how would we compute that? Let's get some specs on our cone. Let's suppose that we start with a cone that has maybe height 10 feet. And let's suppose the radius is, let's just say it's 2 feet. Okay, so we have 2 feet and 10 feet. And let's also suppose that the weight density of water is 62.3 pounds per cubic foot. Okay, so we're going to use that for water. All right, so how do you find the weight of this? Well, you can find the weight at the very beginning, but we want to know what the dimensions of the cone are at the different positions of X as we move up, right? Now, the cone is going to, so it's kind of like we're taking, in some sense, it's kind of like we're just taking subcones, or just parts of the cone, just like this part right here. And imagine that X is even like this distance right here. It's going to be the same. So you can kind of think of it this way, but you could also think of it this way as well. So X is being simply that distance from there to there. Okay, as we're moving down. So that means that this height right here, from here to here, would be, it looks like it's 10 minus X. Okay, so we have X and we have 10 minus X. All right, and we want the ratios of radius to height to be the same, to be maintained. So notice that the radius is 1/5 of the height. So over here, this radius right here is going to be 1/5 of that height. So the radius at position X, so at X, the radius is equal to 1/5 of 10 minus X. Okay. And we can use that to find the volume of maybe the water at position X, right? The volume of that. Look at the volume of a cone, it's 1/3. 1/3 times base times height. So the base is a circle, pi r squared, so pi times radius squared. So 1/25, 10 minus x quantity squared. So that's the base, then times the height. The height is 10 minus x. All right. So this right here would be the volume at position X. And then if you multiply it by that, 62.3 pounds, you get the force at position X, 62.3. So what we end up getting is we get something that we can integrate. As the position goes from 0 up to, so the position goes from 0 up until 10, right? If it's measuring that up to 10, so 0 at the bottom, so 0 to 10. So this integral right here should be able to compute the force, put a little dx there, as we go along. Let's just kind of get some specs. This is 62, so 62.3 over 75 pi. I'm just taking the constants out. I'm going to have 10 minus x cubed, and then a derivative would be 10 minus x to the 4th over 4. And then we're going from, oh, but also because we have a negative in here with the u substitution, we're going to be dividing by a negative. And we're going from 0 to 10. Right, but this negative will allow me to, I can get rid of it and reverse these. So I have 0, 10 like that if I wanted to. Okay, so when I plug in 0, I actually get 10 to the 4th over 4. So 4th of 10,000 would be 2,500. So 2,500. And then if I plug in 10, just get 0. So that bottom part's just 0. So it's really just 2,500 multiplied by 62.3 pi over 75. So that is the total amount of work done, okay, using this particular method. Now, this is not the only method in order to do this. The next video will illustrate another way of combating this problem. Thanks for watching.